Hey everybody, your Friendly Math Tutor here with another lecture video for our AP Calc series. So today we're going to look at Integration and Accumulation of Change Part 2. So last week we dove into Part 1, some of the different types of problems that really focused mostly on accumulation of change. Today we're going to focus on integration. And we're going to look, today is going to be a lot of examples, all right? There's basically going to be 6 types of problems we're going to look at. And we're going to take a look at 3 examples of each. And I'm just going to do a lot of problems today, so hopefully you get to see a lot of different strategies to solve different types of integrals. As always, make sure you subscribe, like this video, check out our Instagram, TikTok, and Facebook for all of our daily videos that'll have to do with this topic this week. Also, check out our Patreon where we have extra worksheets and extra videos there, and some other good things to help you get ready for this test in just about 6 weeks. All right. So the first topic we're going to take a look at today is the second fundamental theorem of calculus. The first fundamental theorem of calculus we went over in the last video was the whole f of b minus f of a. It was a way to evaluate a definite integral. The second fundamental theorem has to do when we're taking an integral. All right, actually, let me add something to this. I totally forgot. These all should be, we're taking the derivative of them. We are not just evaluating the integral. This is the point of the second fundamental theorem, is that we're taking the derivative of an integral, all right? And what ends up happening is the idea that the derivative of an integral, those are inverses of each other. So if you start at a number and you add 5 and then subtract 5, you end up at the same place that you started. So it's like you start at this function and you take the integral of it and then the derivative of it, you end up back at the function. They just kind of undo each other. And what happens is, as long as you have the constant on the bottom, and it is a constant, it doesn't matter what constant it is. Because from the first fundamental theorem of calculus, if we took the integral of this, we would have our capital F function, and then we would plug x into that, and then we would plug in 0, and we would get some number. And then when we took the derivative, whatever the number that was, it would just disappear anyway. So it doesn't matter what number's down here, just as long as it's on the bottom and our variable is on the top. So all that happens here is you end up taking the integral and the derivative. It just brings you back to this function. The only difference is the t's are going to be replaced with x. So the answer is simply just x squared minus x. So this is a very specific problem. You will know it when you are given an integral and then you're asked to find the derivative of that integral. So if we look at this example, this one is slightly different. The constant's not on the bottom. So what ends up happening is we want to make it so that the constant's on the bottom, and we can use a property of integrals. We can take out a negative, so I'll just put that here, and then flip our limits of integration. And then we can do the same thing. So I have negative, and then the derivative of the integral cancels out, and we're left back at our original function sign. But it's just x is replaced in there, so it's just negative sine x. We look at our last example. First of all, something similar happens. I'm going to take out the negative, which means I can flip the limits of integration. But now what we're substituting in is not just x. So this has come up before. It's like the derivative of cosine x is negative sine x, right? But if you have the derivative of, say, cosine x cubed, you can't just say that that's negative sine x cubed. You have to apply the chain rule. So that happens here. Since the function that I'm using, the rule, the second fundamental theorem of calculus, is really designed for when it's just x, whenever I have something more than that, I have to apply the chain rule. So let's first, the chain rule basically says first, just do what you normally do. So the derivative and the integral are going to cancel out. I'm going to be left with this function, the negative from here, e to the x cubed. But since what I have here is not just x. I then have to multiply by the derivative of that, which is where the chain rule comes in. So that's times 3x squared. I can just rewrite this as negative 3x squared e to the x cubed. And that is how we use the second fundamental theorem of calculus. So again, you'll notice that anytime you have an integral and you're asked to find the derivative of that integral, this is when you follow the second fundamental theorem of calculus. Make sure constant's at the bottom. If it's not, take out a negative, make the constant on the bottom. If the function of x on top is not just x, use the chain rule, or just always use the chain rule. Because back here, if I didn't know whether I should use the chain rule or not, just use it, because the derivative of x is 1. The derivative of x is 1. So if you use the chain rule and you're not supposed to, you'll end up just multiplying by 1. So when in doubt, the chain rule is kind of always at play when you're taking derivatives. All right, let's move on to our second type of problem. All right, on to our second type of problem. This time we look at integration by substitution. So before we've taken a look at just some basic integrals where you use the reverse of the power rule or some of the trig functions or e or natural log. But here things get a little more complicated. So you can think of integration by substitution as kind of a way of undoing the chain rule in most problems. So if we take a look at the first one, right, this is too complicated to just integrate normally. So we're going to do something called u substitution. So we're going to make u equal to something. I'm going to choose it to be x cubed plus 1. And our goal is over here, I'm going to say, my goal is to write an integral that has only u's in it. So now that u is x cubed plus 1, this part becomes u to the 4th, right? And I still have this x squared here. So I'm going to have to do something with that. And this is really important. This is the whole crux of the u substitution. You don't want to just memorize the steps that your teacher tells you. You really want to understand why we're doing this so that when you do a problem and you haven't done one in a while, that you can recall why we're doing this. What happens is if we end up, again, this x squared will go away eventually, so just bear with me on that. But if we want to end up with an integral that has only u's in it, we need there to be a du. If we have only x's, we need a dx. So even though you might not completely understand where this dx comes from, usually it takes a higher level calculus or, it's not always very obvious what this even means. And I'm not going to get into that now. What you need to know at this point in your calculus career is that the d whatever variable has to match the variable that we have here, all right, at least in single variable calculus. So if this is x, this is dx. If I want to make it u, I need it to be du. Well, how can I introduce a du into the problem? I can take the derivative. So I do du dx, right? You're used to doing dy dx, just a derivative of u with respect to x. That's just 3x squared. And then I can get, since I want to substitute for dx, I can get dx by itself. These basically can trade places. Hopefully we understand that algebra. Multiply each side by dx, divide each side by 3x squared. So now I can replace the dx with du over 3x squared. Now look what happens. The x squareds cancel out. I have an integral. I'm going to bring out that 3 as a 1/3. Now I have an integral that only has u's in it. And the du matches the u. So it's super important that we understand that. If you have u to the 4th dx, that doesn't have any meaning in single variable calculus. So now we actually do the reverse of the power rule. So I get u to the 5th over 5, but that 5 will get multiplied by this 3 to be 15 plus c. But my initial integral had x's in it, so I want to put the x's back. So finally, I get x cubed plus 1, that's what u is, to the 5th, over 15 plus c. Hopefully you can see that is a 5. So it's x cubed plus 1 to the 5th over 15 plus c. And that's our derivative. That's our integral. So that is integration by substitution. Let's take a look at a different example for number 2. We want u to be x squared in this problem. So if we go over here and we start to see what we have, that means we have a cosine u, all right? We're just going to have faith that eventually that x will be gone, and we can do the integral of cosine u just like we can do the integral of u to the fourth. But I can't have this dx here, so I've got to take a derivative. The reason this gets confusing is because we're taking the derivative in the middle of an integral problem. That's because we want to introduce a du to the problem. So the way to introduce a du is to take the derivative. So du dx is 2x, trade places, like that. So dx is replaced with du over 2x. So notice, integration by substitution, you're doing several substitutions. You're just substituting until you have everything in terms of u. Do a little canceling, factor out the 2, which is really on the bottom, so it's a 1/2. Now look what I have. I have an integral that has only u's and du's in it. They match, so we're ready to take the integral. The integral of cosine is positive sine, so I get 1/2 sine u plus c. And then I substitute back 1/2 sine of x squared plus c. Right, so that is how we use the substitution method. My third example I chose for 2 reasons. I want to show how to do it as a definite integral, how to combine this with the first fundamental theorem of calculus. Also, something tricky happens here, and I want us to be prepared for it. So first, let's just start with u. U, we're going to make x plus 3. And du dx is just going to be 1. So that means du equals dx. So now I'm going to start to substitute. Let's remember, everything has to be in terms of u, including the limits of integration. So I'm going to change the 0 and 2. So these are x values. I want them to be u values. So if I plug in 0 here, 0 in the world of x's becomes 3 in the world of u's. And 2 becomes 5. So now my integral is from 3 to 5. X is still there. U goes here, so that's root u. I'll leave it as root u for now. And dx is du. Seems like I have an issue. In every other problem, when I made that substitution for dx, I got this really nice cancellation. Well, that doesn't happen here. When it doesn't happen, what you want to do is you want to go back to the u, and remember, any way possible, just keep doing algebra, just keep substituting until everything's in terms of u. So I go up here, and u minus 3 is equal to x. Well, that means this x can be replaced with u minus 3. So I get the integral from 3 to 5. I get u minus 3, and then this is root u, but that root u is really u to the 1/2. Which means I have the integral from 3 to 5 of, if I distribute, I get u to the 3/2 minus 3u to the 1/2. Both of these should have a du in it. We talked about the importance of that. So now we're ready to integrate because we have everything in terms of u. So let me see. I'll get rid of this problem, and I'll go up here. So the antiderivative of u to the 3/2, add 1 to the exponent, so I get u to the 5/2 divided by 5/2 is like multiplying by 2/5. I got minus u to the 1/2, add 1 to that, I get u to the 3/2, divide by 3/2 like multiplying by 2/3, and the 3's cancel. So I get 2u to the 3/2. And that is all. I don't have to back substitute. I don't have to put the x's back in because I changed the limits of integration to u values. So now I can just integrate from 3 to 5. I don't think this is a very, 3 and 5, you're not going to be able to do the square roots of them. So I'm just going to leave it as 2/5, 5 to the 5/2 minus 2 times 5 to the 3/2 minus 2/5 times 3 to the 5/2, and then minus a negative, so I'll get plus 2 times 3 to the 3/2. So you could throw that in a calculator and figure out what it is. But the thing that I really wanted to focus on was two things. When you have a leftover x here, go back up to this and you can solve and do an extra substitution. And I really think it's good practice to change the limits of integration based off of this so that you have only u values and then you don't have to back substitute. You can just evaluate the integral in terms of u and you get the same numerical value. All right. Okay, let's move on to our next type of problem. All right, let's take a look at our third type of problem for today. We're going to be using integration by parts. So integration by parts is more of a way to undo the product rule. It actually comes from the product rule. If you were to bring this over to this side, you would kind of see that you have like u dv and v du. That's kind of like the product rule, like f prime g, g prime f. I'm not going to get in this video as to like exactly where it comes from. There's plenty of other things, ways you could look that up. But what I'm going to focus on in this video, again, is just about like showing you how to do certain types of problems. So what we have is we're typically going to have a product of two things is generally where you're going to use integration by parts. And u substitution isn't going to work. So like here, if I make you never want to make u x because like in u substitution, because like all you're doing is changing the variable. It doesn't make the problem any simpler. So you don't really have any options here for u substitution. So now we're going to do integration by parts. So for integration by parts, you need to choose something for u, choose something for dv, and then that u is going to lead to a du, and that dv is going to lead to a v. So what I would do here is, in this case, I would make u equal to x. Because typically when we have a power function, we want to make that x, make that u, and then make like a trig function, we would make dv. But that's not always the case. There's kind of like a hierarchy that we can look at. But for this one, it's going to make most sense to make u x, because when I take du, I'm just going to get dx. The derivative of x is 1. dv, I'm going to make sine x dx, and v is the integral of that. So that's going to be negative cosine x. And then I simply just use the formula. So the integral of u dv is uv, so negative x cosine x minus the integral of v du. So this negative I'm going to make there to make it a plus, and that's cosine x dx. This integral hopefully will be something that we can now integrate. So I get negative x cosine x. The integral of cosine is positive sine. And then I have, obviously, it's an indefinite integral, so I need my plus c. What happens is sometimes this integral here needs integration by parts again. That's the next two problems. One of them, something kind of special is going to happen. I'm going to go over that here. But in this one, instead of going through that over and over and over again, it can be a lot of algebra. I'm going to show you a shortcut to this called tabular integration. So the way that works is you're going to use it whenever you have a power function here, and then this function is either e to the x, cosine x, or sine x. They're the three situations where it works best. So tabular integration looks like this. You're going to make a column for u and a column for dv. You're always going to make u the power function, and you're always going to make dv the other one. I'm not even going to write the dx anymore. This is a shortcut. So you're going to first derive this down to 0. This is why it has to be a power function. You can't make that e or cosine. They'll never go to 0. Power functions will always make their way to 0 if you keep deriving them. So the derivative of x cubed is 3x squared. The derivative of 3x squared is 6x. The derivative of 6x is 6, and I get to 0. Then I go over here and I keep integrating this function, and so that it matches with the number of times that I had to derive this one. Well, e to the x is simple because the integral of e to the x is e to the x, so I'm just going to keep writing e to the x. And then I'm going to match the first column or sorry, the first row with the second row with third row with fourth row with fifth row. The point of the 0 tells me when to stop. And then you're going to write a plus, minus, plus, minus. So you start with plus and then you just alternate signs. That's because in integration by parts, this negative gets distributed, so it keeps like flipping the sign back and forth. And finally, your answer is just you multiply them together. So this is x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6e to the x plus c. So that saves us doing integration by parts several times. So it's a worthy shortcut if, again, you have a power function here, x to any power, and e to the x cosine x or sine x, this will work nicely with. Okay. All right, I'm going to erase that because I went over into my space. I'm going to need some space for this. This is what I would call a circular integral or circular integration by parts. But in the beginning, tabular integration isn't going to work because you'll never be able to derive either of these down to 0. So what you want to do is just get started with regular integration by parts. So I'm going to make u e to the x. I am going to make dv cosine x dx. And so that means du is e to the x dx, and v is sine x. So if I use the formula, we are going to get e to the x sine x uv minus the integral of v du, so e to the x sine x dx. And what we end up with is, it looks very similar, right? It's just integration by parts again. So I'm going to do another little integration by parts over here. I'm going to make u e to the x dv equal to sine x dx. Du is e to the x dx, and v is negative cosine x. That is the integral of sine. So now I'm going to go back. So I have this e to the x sine x here. Then I have a minus. Now I'm going to do integration by parts again. So I have uv. Well, that's negative e to the x cosine x times this negative is a plus e to the x cosine x. Remember, there was a negative there, though. So then what happens is I end up with a minus the integral of e to the x negative cosine x. So now that's going to turn into, actually, hold on. That's actually going to stay a negative because I'm going to be doing, there's a minus in the integration by parts. Then the minus and negative turns into a plus. And then this minus here gets distributed and turns it even into another negative. I probably should have done parentheses and all, but I didn't. So I apologize if anybody got confused on that. But if you really write it out, it definitely ends up with a minus. It's like a triple negative. All right. Well, this presents a problem because at first it's a problem, and then it's actually something great happens. The first issue is, okay, well, now I got to do integration by parts again, but it's the same one that I started with. So this is where it turns into something cool. I can say this whole thing is just equal to the integral that I've been trying to solve this whole time. And I could just add this over, so they get 2 times the integral that I'm trying to solve. And I kind of solve this indirectly. Because my goal was to just solve this integral. What do I can solve that integral? Simply by just dividing by 2. So I'm just going to get rid of that. Divide this by 2. Slap a plus c. And I've got my answer. I was able to, so it's called a circular integral. It's basically going to happen whenever you have e to the x combined with either cosine x or sine x. And when you do it a second time, you should end up with the same integral that you were trying to find. So you just make sure that you set it equal to that. You move it to the other side and divide by whatever coefficient is there. And now you have figured out what this integral must equal. Okay? All right, let's keep it moving. All right, let's move on to our fourth type of problem today, integration by partial fractions. So if we take a look at this, we've got a fraction. The integration by parts isn't going to work. Use substitution isn't going to work. So another option you have is partial fractions. So what we're going to do is we're going to think about what's called the partial fraction decomposition. So this is 1 over, I'm going to factor this. This is x minus 5 times x minus 2. So partial fractions are the opposite of getting a common denominator. I'm trying to figure out which partial fractions that when I get a common denominator, when I add them together would give me this as an answer. So I'm going to have some constant over one of the factors and then another constant over the other factor. And I'm going to do some algebra. I'm going to multiply through by this denominator, which means it's going to, so I'm basically doing this. So this cancels out, I'm left with 1. This goes away, so I'm left with a times x minus 2. Plus this cancels, so I'm left with b times x minus 5. One thing you could do here, I could just let x equal to 5, so then that makes all this go away. And if I plug that in here, I get 5 minus 2 is 3, so a is 1/3. And then I could make x equal to 2, so that all this disappears. And then I get negative 3b equals 1, so b equals negative 1/3. So if we go back up here, now we have two separate integrals. This can be written as 1/3 over x minus 5 dx. And then if this is negative 1/3, I could think of it as minus 1/3 over x minus 2 dx. So I've used partial fractions and then the fact that I can take integrals and separate them by addition or subtraction. And now I have two pretty easy integrals to evaluate because this is just 1/3 the natural log of x minus 5. And then this one is just 1/3 the natural log of x minus 2. Plus. All right, so we do the partial fraction decomposition, and then in this case, since they were just single linear factors, we could kind of use the shortcut of picking values of x to get a and b, and then the integral is just in these cases, you're always going to use ln. But now let's take a look at a little bit of a harder case. So in this one, we're going to have x squared plus 11x over x minus 1 times x plus 2 squared. And we're going to end up having a over x minus 1. But we have a repeated linear factor, x plus 2 squared. So then I'm going to have b over x plus 2 plus c over x plus 2 squared. So that's called a repeated linear factor. It's going to make the integral a little more challenging and just a little bit more work to find a, b, and c. So then what's going to happen is I'm going to end up with x squared plus 11x equals. Well, if I multiply everything by this common denominator, the x minus 1s will cancel, and I'll be left with a times x plus 2 squared. Here, the x plus 2 will cancel, and I'll be left with b times x minus 1, x plus 2. And then here, the x plus 2 squareds will cancel, so I'll be left with c times x minus 1. Again, I can plug in values, so I'm going to make x equal to negative 2. If I make x equal to negative 2, this one and this one are gone. I'm left with negative, actually let me plug in negative 2 here. So I get 4 minus 22 is negative 18. If I plug in negative 2 here, I get negative 3c. So c equals 6. So let's remember that. I could plug in 1. 1 will make both of these go away, and if I plug 1 in here, so if I make x equal to 1, if I plug in 1 here, I get 12. And if I plug in 1 here, I get 3. Yeah, 3 squared is 9. 9a. So a is going to end up being 4/3. Then what happens is I don't have a nice way to get b. So what I would do is I would just pick another value at this point. We could expand it and do it that way. I would just pick another value. I'm just going to pick x equal to 0 and just see what happens. So I plug in 0 here and I get 0. If I plug in 0 here, I get 4 times a, which is 16/3. If I plug in 0 here, I get -1 times 2, so I get -2b. And if I plug in 0 here, I get -1 times c, but that's -6. So I can add the 6 to the other side and do 6 minus 16. Or no, actually, I'm going to do this. I'm going to add 2b to this side. And then 16/3 minus 6, 16/3 minus 18/3 is -2/3. So if I divide by 2, b is -1/3. All right, so I'm going to erase some over here so we can finish this problem. And what happens is I now split this up into 3 integrals. The first integral is if a is 4/3, I have 4/3 over x minus 1. B is -1/3, so I have minus the integral of 1/3 over x plus 2. And c is 6, so I get plus the integral. This is what I'm going to do here. These two I'm going to be able to use natural log, but I will not when it's x plus 2 squared, when you have a repeated linear factor. So I'm going to think of that as 6 times x plus 2 to the -2. These all should have dx's in them. So now this one ends up just being 4/3 the natural log of x minus 1 minus 1/3 the natural log of x plus 2. Finally, here I can use the reverse of the power rule. So add 1 to the exponent, so x plus 2 to the -1, and divide by -1, so it becomes minus 6. X plus 2 to the -1 is just over x plus 2, and then I get a plus c. All right, so when you have a repeated linear factor, you have to go the extra, like plug in another value to solve. And then you also end up, when you integrate, only when it's a single linear factor are you going to be able to just use ln. It's when you have a higher power here, you're going to have to just use kind of the reverse of the power rule. All right. Okay, let us move on. All right, 5th type of problem, improper integrals. So improper integrals, I'm doing 2 of these. So you can see the 2 different ways to know, or I guess to recognize when to use an improper integral. The first and easiest way is if you just see infinity as one of the limits of integration. That's an improper integral. This is like saying whatever function this is, what's the area under the curve from 2 to infinity? Well, that seems like it should just be infinity. But what happens is that area, if you went from 2 to a million or 2 to a billion, that area could start to converge. It could kind of have a wall. It could have like a number that it'll never go past. So we say that it converges and we actually give it a numerical value. It's also possible that it does grow without bound. And in that case, we would just say that it diverges. So let's see what we do. We are going to turn this into a limit. So we're going to take the limit as r. You probably use maybe different letters depending on the book or what your teacher did. I'm going to use r. So I just basically replace infinity with r and take the limit as r goes to infinity. I'm going to think of this as x to the -3. There definitely should be a dx here. And then I just evaluate this integral. So I got the limit as r goes to infinity. Well, I use I just used the reverse of the power rule. Add 1 to this, so I get x to the -2. Divide by -2, and I'm going to evaluate it from 2 to r. So if I go up here, I got the limit as r goes to infinity. I'm going to rewrite this. I'm going to move this to the bottom so that this is really -1 over 2x squared. If I plug in r, I get -1 over 2r squared minus f of b minus f of a. When I plug in 2, 2 squared is 4, so it's -1/4, so it's like +1/4. Nope, that's 1/8. 2 squared is 4, and 4 times 2 is 8. All right. Then what happens is I just evaluate this limit. Well, that limit at infinity, that's 1 over infinity, which that means it goes to 0. So this goes to 0, and the limit of a constant is a constant. So the answer to the integral is 1/8, which means we could say that the area converges to 1/8. Another example of a problem that doesn't immediately look like it's improper because we have a number here and a number here. This one was obvious, it had infinity. So what you have to do now is when you have a fraction, you want to test your limits of integration, or really you want to just look, does the function that we call the integrand, does the integrand have an undefined value, first of all? This one does. And is that undefined value either at one of the limits of integration or somewhere in between? Well, this is undefined at 1, can't divide by 0 when x is 1, and that's one of the endpoints of our limits of integration. So therefore, this is also an improper integral. So I'm going to do it in a similar way. I'm going to take the limit as r goes to 1 from the right, because between 1 and 2, I'd be approaching 1 from the right side. Not sure why I was pointing down. I was meant this way. So then that would be the integral from r to 2. Again, I'm going to think of this as x minus 1 to the negative 2 dx. So I have the limit as r approaches 1 from the right. The integral of this, I'm going to add 1 to give me negative 1 and divide by negative 1. So it really becomes negative 1 over x minus 1, evaluated from r to 2. So I'm going to do the limit as r goes 1 from the right of negative 1 over, if I plug in 2 to this, I just get negative 1. Minus a negative is going to be plus 1 over r minus 1. And this limit right here is obviously negative 1, but if we take a look at this, what's going to happen there is if you approach r, if r approaches 1 from the right, this is 1 over, so a really small positive number, and 1 divided by a really small positive number is a really large positive number. So this is pretty much infinity. So this one equals infinity. So this is a type that we would say diverges. This is an example of a vertical asymptote. And what happens is it is possible for that area to diverge or converge. In this case, it's diverging. That area is just getting bigger and bigger and bigger. So we say either the answer is infinity, or the type of question, you could just say that it diverges. All right, let's keep it moving. All right, we move on to the sixth and final part of this lecture, and it's a review. So I picked out 3 problems, the 3 different types of problems that we've already talked about. And each one of them, actually 2 of them in particular, have kind of like a wrinkle to it that I wanted, it's like an extra thing that I wanted to go over. So we take a look at this problem. U substitution doesn't really look like it could work. Integration by parts doesn't really make sense here. Since this x squared minus 4 factors nicely, it looks like it's partial fractions, which it will be. But in the beginning, it's not, because we have a larger degree on top than we have on the bottom. Partial fractions isn't going to work that way. Partial fractions, you need a smaller degree on top than on the bottom. So if the degrees are the same or larger on top, what you're going to want to do is long division. So over here, I'm going to do a little bit of long division. So x squared minus 4, and then I have x cubed plus 0x squared plus 0x plus 1. X squared goes into x cubed x times x squared is x cubed minus 4x. And then I get rid of this. I get a positive 4x plus 1. And this is the key right here. I'm done. There's no way x squared can go into x. So what I end up with is this function can be written as x plus 4x plus 1 over x squared minus 4. So this is the quotient plus the remainder over the original divisor. This is what you would have learned back in like Algebra 2 or Pre-Calc as a way to write this function. So now what I have is the 4x plus 1 over x squared minus 4. That part I can use for partial fractions. So I'm going to do this. I'm going to factor it to x plus 2, x minus 2. Then I'm going to have capital A over x plus 2 plus capital B over x minus 2. Clear the denominators. So I'm going to end up with 4x plus 1 equals A. The x plus 2 will cancel times x minus 2. The x minus 2 will cancel here times x plus 2. Make x equal to negative 2. That gets rid of that one. So this is negative 4. Well, if I plug in negative 2 here, it's negative 8 plus 1 is negative 7. If I plug in here, I get negative 4a. So a is 7/4. And then over here, if I make x2, that gets rid of this one. So I get 9 equals 4b. So b is 9/4. So finally, I have the integral of x dx, that's this part, plus the integral of 7/4 over x plus 2 dx, plus the integral of 9/4 over x minus 2 dx. And finally, this is x squared over 2 plus 7/4 ln of x plus 2 plus 9/4 ln of x minus 2 plus c. All right, so you use long division first. On the remainder part of it, you do partial fractions. Then you put it all together. Don't forget this quotient part. We still have to integrate that. And we end up with a couple natural logs and just the reverse of the power rule. All right, so that is a partial fractions problem where you have to do long division first. Okay? All right. Let's move on to number 2. So I'm actually going to erase this because I went into that space. Number 2, we see an infinity. So an infinity is just going to tell us that it's an improper integral. So what I want to do is I want to take the limit as r goes to infinity and make it from 1 to r of 3 over x dx. Well, here I have the limit as r goes to infinity. The integral of 3 over r is just 3 ln, 3 over x is 3 ln x from 1 to r. Then I have the limit as r goes to infinity of 3 ln r. Well, I know r is positive, so I don't need the absolute value anymore. Minus, well, the ln of 1 is 0. So I just get 3 ln r. And if we remember what the natural log function looks like, it goes like this. It does not have a horizontal asymptote, so it's going to go up forever. It levels off a lot, but it still is always trending upward. So therefore, this goes to infinity. So we're going to have another one of those diverging areas. So the answer to this is infinity, or it is an improper integral that diverges. All right, last problem. This one is an example of a u substitution, but it's got a little bit extra. It's a trig integral, so I did want to go over one of those today. So it's at its core, it's a u substitution. So we're going to make u equal to something. The cool thing is that the derivative of sine is cosine, and the derivative of cosine is negative sine. So it looks like we could make u either one of them. But it turns out that we're really going to have to make u equal to, well, let me actually think about it. And let me tell you kind of my thought process here. So if I make u equal to sine, that means my du is going to be cosine. So one of these cosines is going to go away. And the other cosine, I'm not going to be able to do anything with it. I'm just going to have this extra cosine there. But if I make u sine, oh, I just said that. I just said if I make u sine and derivative of cosine. If I make u cosine, the derivative of cosine is negative sine, and one of these sines can go over with the dx to be part of the du. If this doesn't make sense, you'll see when I do it. And then I'll have a sine squared left, and that sine squared I will be able to get rid of using a trig identity. So I am going to make u cosine x. So that means du dx is equal to negative sine x dx. Oh, not dx yet. just sine x. And then I will get du over negative sine x is equal to dx. So when I go to substitute, I'm going to have a sine cubed, and then u is cosine, so I have a u squared, and dx is du over negative sine x. Well, this seems to be an issue because this is only going to cancel out with one of those. So I have this negative that I bring out in front. But what happens is, this is a sine squared. Well, that's fine. If I had made u sine, I would have been left over with just a cosine, and there was nothing I could have done about that. But if I have a sine squared, I can use the trig identity that sine squared plus cosine squared equals 1. So sine squared is really just 1 minus cosine squared. That's our Pythagorean identity. But cosine is just u. So this really is just 1 minus u squared times u squared du. And then I can distribute. So I have u squared minus u to the 4th du. And then even I can distribute the negative. So I get negative u squared plus u to the 4th du. And then I can integrate pretty easily. So I will have negative u cubed over 3 plus u to the 5th over 5 plus c. And finally, u is cosine. So I get negative cosine cubed x over 3 plus cosine to the 5th x over 5 plus c. And that is the answer. So that's called a trig integral. But I'm doing it using u substitution. The key is to just kind of figure out, do I want to make u cosine or do I want to make u sine? So you just kind of play around with it. If you end up with an odd power of one of them left over, you won't be able to do it. You want to be left over with an even power so that you can use a trig substitution, and then you'll be able to get everything in terms of u. All right. I hope that was helpful. That is the end of this video. As always, please like this video, subscribe, check out our Patreon, check out all of our videos on TikTok, Instagram, and Facebook. And I hope you are back for our video next week where we'll move on to Unit 7. All right. Bye.